So again, for the very last topic in our class and in the MedChem chapter, we want to talk about lead optimization, which, like we said, is often the main job of a medicinal chemist. And that's going from the hit compound that you find in your screening that becomes your lead, and then you optimize it so that hopefully it becomes a nice drug. Like we'll talk in the next few minutes. We'll talk about what kind of things you could replace a certain functional group with. Like thiophene, believe it or not, is often, as far as drugs go, interchangeable with benzene ring. And then if there's a spot in your molecule that is very prone to, say, cytochrome P450 oxidation and it loses its activity too quickly, you could often replace the hydrogen at that location with a fluorine, and you could do stuff like that as a medicinal chemist. And of course, the goal is going to be to increase the therapeutic index, which is sort of the balance, the difference between like when the drug becomes toxic to you or even lethal to you, and when the drug gets to give you the maximum amount of the desired effect of the drug. So it's often given in a ratio, LD50, which of course you want that to be small, right? I mean large, right? Like um, if you have a small LD50, that means even a small amount of this drug could kill you, so that's not good. And ED50, you want that to be rather small, right? Like small amount of drug, you want that to have an effect, a good effect on you. So you want this ratio to be rather large. So that's the therapeutic index, right? The larger the therapeutic index, the greater the margin of safety, because the difference between toxicity and good efficacy is big. Um, and uh, for like diseases that are not life-threatening, you want that to be like super large because it's not worth it to potentially risk a lethal or fatal side effects if the disease you're trying to treat with the drug is not gonna like kill you or anything. It's just an inconvenience in life or something. Then there's not much tolerance of a small therapeutic index. But when it comes to things like terminal cancer or something like, or cancer in general, things that could kill you, right? Then it's kind of acceptable if the therapeutic index is. And so what are the types of structural modifications people make? Homologation is one way you could sort of mildly change the structure, and that's just exactly what it sounds like. You just elongate the chain somehow. And then there's usually an optimum sweet spot, right? Like if you elongate like maybe by 8 carbons, you get increasing potency, but if you go past that, maybe the potency starts to decrease or something like that. So one way you could kind of explain this, maybe from the pharmacodynamic, remember that's what the drug does to the body perspective, is maybe the hydrophobic pocket to which the drug binds. There's like extra space that you could occupy, right? If you increase the chain length by like another methylene group or something, maybe you could more effectively fill that pocket, right? Like the pocket that the drug fills, maybe you can make it a little bigger, effectively fill that pocket, and that would increase the hydrophobic interaction, and that would increase the potency. But obviously, if the drug gets too big to fit into that pocket, then it's not going to bind well. So that would uh, result in maybe pretty drastic decrease in potency. Pharmacokinetically, right? Like it could be about the lipophilicity, because remember, pharmacokinetic has to do with a lot of things, but one of those is like how well does it dissolve, how well does it get absorbed, how well does it distribute, right? If the lipophilicity is not enough, by elongating the lipophilic chain, you could make it a better drug because maybe the increased lipophilicity might mean that it crosses the cell membrane better. But if it's too lipophilic, of course, it's never going to dissolve in water or any sort of formulation, and it would have a solubility issue. So you have to hit the sweet spot. So here's one interesting example. Um, if you just increase the chain length from starting from methyl to like much longer alkyl group on this simple looking compound, you can increase the sort of the antibacterial activity. And a lot of the like medicinal cough drop or throat lozenges, those um, actually contain the hexyl um, compound, where this 6 carbon chain hanging off here, because that happens to be the optimal potency for that antibacterial activity that it can confer. Um, when it comes, and then like for another activity, spasmolytic activity, right? Like there's a different sweet spot down here, but again, it just drops after it gets to a certain sweet spot. Branching tends to make things less lipophilic than straight chains, so that is kind of seen in these ice branched version of alkyl groups. So that kind of naturally leads to chain branching. Tends to lower potency if the lipophilicity is important, because again, that, like we said, it tends to lower the lipophilicity, and usually, in my experience, lowers the solubility too. Um, and sometimes it could make it more selective, but sometimes it could make it less potent, depending on how it binds to the receptor. Like if you compare these 3 compounds that are different in chain length as well as either presence or absence of branching, right? It's interesting to compare the bioactivities of these. One compound uh, can treat like spasm and stuff stuff like that. It also has antihistamine activities. Um, but if you uh, add a branch to it, or actually this is elongated also by 1 carbon, right? Like it now has a sedative effect. Now, if you add an extra methyl to branch it, then you could reduce the sedative effect if that is not the activity you want to confer. That's a bad side effect, right? Like it makes you dizzy or drowsy or something. But now you can enhance the um, plasmatic active anti-spasmodic activity and whatnot. So like what this tells you is that first of all, all these 3 are known to bind to different receptors, or at least different subtypes. And again, that's because the little bit of branching makes it not very bindable to the other receptor, but it can still bind to this other receptor very well and stuff like that. So chain branching is a nice way to modify your lead. Another one that people often do, and this might be the biggest category of the 4 that we present here, in that's swapping out certain functional group with bioisosteric compounds. Isosteric just means like having the same electronics structures. Bioisosteres are not, they don't necessarily have the exact same electron structures as the parent original functional group, but tend to function the same way anyway in a biological system. So you can the classical isosteres are kind of like this. At least Lewis structure-wise, methyl kind of has the same electron structure as amine and OH, but they're not always swappable, as you can imagine, right? Like there's absence and presence of hydrogen bonding and so forth. Some of these simply isosteric because sort of the size is kind of the same. Your textbook also has a figure listing different bioisosteres. These, everything on this slide kind of could be a substitute for carboxylic acid, believe it or not. And some of these groups, right, like look very different than carboxylic acid, but electron structure is kind of similar, and the way that the charge is distributed is kind of also similar, or the way that it can do hydrogen bonding is kind of similar. And for those reasons, all these different functional groups tend to be a good replacement for carboxylic acid to see what happens. Some of these, of course, have different, very different pharmacokinetics. So the charge would be different, so the solubility and the way it dissolves and absorbs and distributes might be different, or maybe the way that it responds to metabolic oxidation or conjugation might be very different. So for all those reasons, it's worth swapping out with a bioisosteric group. And so these are all considered bioisosteric to um, uh, carboxylic acid. These are also sort of a bioisosters. Believe it or not, you can swap these groups out, carbonyl group for these groups to have similar carbonyl effect, or we talked about carboxylic acid substitute, but here's amide substitute, ester substitute. Believe it or not, these things kind of work similarly to hydroxyl groups because of the presence of hydrogen bond donor and acceptor. And These are different isosters, bioisosters. Sometimes you might be surprised to see something like this would be a substitute for benzene, but it just kind of occupies a similar amount of space. And sometimes you could do a ring to chain swapping and occupy still similar amount of space and have similar effect still. Similar pharmacodynamic, but maybe the pharmacokinetic could be improved by swapping out things. And spacer group, chain to ring spacer group is another approach. And so here's an actual real life examples of bioisosters where they could have a ketone or this nitrile group and have similar pharmacodynamic activities, or this X group could be swapped among all these fairly different looking groups and have similar effects and so forth. Um, so why do we do this bioisosteric replacement? Sometimes changing the sides, shape, electronic distribution just a little bit results in effects that are just desirable. Usually for pharmacokinetic property changes is what you're going for. So sometimes it results in pretty different structural changes, right? That results in different pharmacokinetic properties. Could it result in a fairly different pharmacodynamic properties if it changes the way it interacts with receptors quite a bit different. And of course, the way it changes metabolism is kind of the part of pharmacokinetic parameters. But anyway, this is kind of about tinkering these properties to have just the right potency and tolerable toxicity and pharmacokinetic properties and whatnot. So, a lot of times you have to make multiple swappings, multiple alterations, right? And then the question as a medicinal chemist, of course, is where on the molecule do you do these bioisosteric replacements typically? Where do you think? If you answered pharmacophore, that's usually not the case, because if you change the pharmacophore, remember by definition, you probably are going to lose the activity, but often you want to change the oxophoric groups. And the last category of change that we might cover, the medicinal chemists might do, is to make the molecule more conformationally rigid. And that can have a very great impact, especially pharmacodynamically. If, say, like there's a sort of unnatural conformation or like high energy conformation that it's uncomfortable for the drug molecule to take, but that uncomfortable shape or conformation is what is more biologically active or what actually fits in the receptor better or something like that, then you want to make the molecule more rigid or constrain the conformation in that high energy state or conformation state. Now, just because the changing the um, uh, conformation conformationally constrained molecule loses activity, let's say, that doesn't necessarily mean that conformation is necessarily wrong or incorrect or proper for that binding to the receptor. It could just mean that the extra atoms you added to make it more rigid are just not compatible or something. So you can't always jump to conclusions when you do conformationally rigid analogs. But here's one example, right? Like this molecule uh, uh, is uh, is a good um, compound to bind to this particular calcitonin gene-related peptide receptor. For this discussion, you don't need to know what that is, but I hope you could tell that this molecule has a flexible bond right here that could this single bond could rotate in any way you want, right? Same with this V bond as well, but these are two dominant, two fairly different conformations that it could take. One of the ways you could study which of these might be the preferred conformation is to make the conformationally rigid analog. And if you compare these two, they look pretty similar, except you made a ring right here so that this amide is more conformationally rigid. If you make the ring right here or right there, right, to make it more rigid, then you can kind of constrain the molecule into this type of conformation. It turns out that this compound on the right, analog on the right, has much lower affinity than the original compound, which means that this is likely the preferred conformation for this receptor. Hopefully that logic makes sense to you. Here's another example that by making this part of the molecule more rigid, right, you were able to reduce the adverse side effects. And then that's probably because as this acetyl group can flap around, right, move around a bit, this bond is rotatable, right? Like it could target some other receptor that leads to those side effects. But now that it's rigid now, those um, other receptors are not targetable anymore. I hope that makes sense. Okay. So sometimes conformational rigidity can lead to decreased side effects or decreased toxicity. So there's those benefits, right? Like conformational constraints can lead to reduced toxicity, and sometimes it could lead to binding to like metabolizing enzymes like cytochrome P450 so that it's more metabolically stable, so you could have longer effect, so you don't have to take as much of the drug. And sometimes even the potency increases just because the drug can cut through or go through the cell membrane better. And the way to kind of picture this is if you have a flimsy knife that can like flop around in its conformation, so to speak. It's kind of hard to cut through butter or something with that, right? But like if you have a very rigid knife, right, like or conformationally constrained knife or molecule that can cut through things a little bit better. And same with going through